readjust ourselves. Maybe I won't touch that. Thank you all so much for coming. I know I hear it's the middle of your finals season, so thank you for coming to an extra lecture. I'm super happy to be here, and thanks so much to Professor Yoon for the invitation. And what I wanted to do today is to first do a little bit of self-advertising in terms of just who I am at the University of Michigan. So I run the Laboratory for Air Transportation Infrastructure and Connected Environments. It's a research group that's within the Aerospace Engineering Department, although we have students also from civil engineering as well as operations research, because you'll soon see that air transportation is quite interdisciplinary. What I'm going to do today is just walk you through two projects. One will have to do with the air transportation system as it exists today. And the next will be the air transportation system as we can imagine what it might be in the future. Okay, so it's going to touch on a couple of different methods. So if you like math and methodologies, hopefully there'll be something in here for you. And it'll also touch on different applications of those methodologies. Okay, so I'm just going to leap right into the first work. So this is really work that's led by my PhD student, Hal Chen, as when we collaborating with Dr. Alex Estes at the University of Maryland. So what is the initial motivation? And I'm also hoping, I don't really know what you all work on for your research and so on, but I'm hoping that there are common threads that you could potentially exploit even for your own research. So in the United States, we are looking forward in the next 15 to 30 years about what our air transportation system could look like. And the FAA, the Federal Aviation Administration, has released this nice booklet that says, so I've just pulled a couple of things from the booklet here. We want to do predictions to help with decision making, and we want to manage uncertainties and so on. So this is a nice vision, but whenever I see and read something like this, it really inspires me. But then I'm also like, what does that mean? Like specifically, like what do you like? How would we implement, or what is the actual method and algorithms and so on? So let me take you through a journey of how we, as researchers, try to bridge kind of vision and reality in terms of the research and development that we try to push. Okay, so keep this in mind. We want to do predictive things, and there may be uncertainties when we try to do that. How can we manage our decision-making under these heavy uncertainties? Okay, so going straight into the air transportation motivation. So one of the main reasons or factors for why your flight is delayed is due to arrival airport capacity issues. Okay, so for every airport, it has standard capacity. So for, in this hour, this airport can land 80 aircraft per hour or whatnot. Okay, same thing at Incheon, right? In the optimal north flow or south flow configurations, Incheon can land a certain number of aircraft per hour. When there's bad wind conditions, well, I guess maybe you all never have bad wind here because Incheon doesn't have crosswind runways, but in other parts, so this is actually Detroit Airport, the dominant wind directions are this way, but sometimes the wind blows this way, which means the planes have to land on these two runways. And when we land on these two runways, the capacity drops by about half, which you can imagine is going to result in delays and so on. So this is very well known. It's very well studied. And in fact, there's kind of a large chunk of literature on trying to predict what might be the active runways and what might be the airport capacities at these airports. In fact, it's so mature that companies have taken the research and actually implemented them as products. So here's one example. So FlightAware actually has this product called FlightAware Foresight. And if you can Google it and go on it now, it's actually kind of fun because you can, it also works for international flights. So you can search a Korean Air flight if you'd like. But let me show you an example of what one of these prediction tools look like. So this is a screenshot of the arrival runway predictions. And this was actually for a flight that I was on from Boston to Detroit Delta 2222. And if you can see, this is a pretty boring prediction. In fact, it's quite certain that I'm going to land on runway 21. So this prediction is, there's not much uncertainty in this prediction here. And I did land on 21 left, so it was correct. But now, actually, let's take a Korean Air flight. So this is a flight that I randomly found from Seoul to Sydney, okay? And now, if you take a look at the predictions of what runways will be active for this flight, so it's probably about maybe 2 hours from its destination at the moment. And if you look at the predictions, what you see is that there is significant uncertainty in the way that we usually think about uncertainty, which is in this vertical direction. That's the uncertainty in terms of what runway I might land on or might be active at this time. But actually, even across time, you see that there's changes in that uncertainty. So basically, there's uncertainty, and then there's uncertainty of your uncertainty. Okay, so there's distributional shifts, essentially. Because all of these machine learning models, at the end of the day, their output is a distribution. Okay, even if it gives you a number, it's the mean of the distribution or something. So it's a distribution output. The question that we had is, well, how do I make air traffic management decisions when I'm making decisions based off of a prediction model, but that prediction model could be wrong? Maybe there's a distribution shift, or maybe even worse, you thought it was going to be a nice Gaussian random variable, but it turned out to be bipolar. So that's a misspecification of the distribution family, right? So keep this in mind, because I'm going to actually talk just briefly about air traffic flow management. Some of you might be very familiar with this, others may not be. Basically, when there is a imbalance, so 40 aircraft wants to land at an airport that can only land 20 aircraft per hour, you have to delay 20 aircraft, right? You have to assign some proactive delays. Now, would you rather assign delays while it's still on the ground with engines off, or would you rather kind of get to the airport and then have to do airport holding? So generally, we try to make sure that if we have to delay somebody, we try to delay them on the ground. It's less costly, safer, and so on. And we do a pretty good job. So what I'm plotting here is in actual delay minutes in the United States. Everything that you see in blue is ground delay. Everything that you see in red is air delay. So we do a pretty good job of kind of managing things to be on the ground. But actually, when you look, so as a researcher, when I look at this plot, I ask two questions. Okay, the first question is, how do I take more of the red and make it blue? In other words, how can I make better predictions so that I can assign more strategic ground delays? Okay, that's question number one. Question number two, maybe the more obvious question, how do I just reduce the height of the bars? Okay, so, and maybe this is a controversial statement. Some delay is good, because if you have no delay, what I think is you've overbuilt your system. So your system can handle 100 aircraft, but you only have 50 aircraft that wants to land. You're not going to have delay, but I would argue you've overinvested where you didn't quite match the investment of your capital to the actual demand. So some delay is okay. What we don't want is excessive delay on top of what we actually need, okay? So what do I mean by that? Let's say you're flying from Incheon to Busan, and Busan has bad weather, and you say, oh, it's going to be bad weather for 3 hours, so delay for 3 hours. But then 1 hour later, Busan's weather improves. Now you've kind of unnecessarily assigned 2 hours of ground delay to this aircraft. And it's very difficult to undelay a flight. Airlines do not like to do that because if you see your flight's been delayed by 3 hours, you might leave the airport, you might go shopping, right? And then you can't undelay that by 2 hours because then passengers may not even be there. So basically it's a question of over conservatism versus under conservatism, right? You don't want to be under conservative. That'll get you a lot of red airborne delays. You don't want to be overly conservative because that'll get you way too much blue that you didn't. So keep that in mind. And just for folks who may not come from air transportation, let me show you what happens when air traffic management is not effectively done. So this is one of the largest airports in the US. It's Dallas-Fort Worth. And here's an example of a day where the weather, so this is all rain over here, and this is the airport. So the weather was much worse than anticipated. So what happens is you get these holding patterns right outside of it because they're not able to land. So all these arrival flights have to hold outside of the Dallas airspace and wait for this thunderstorm to pass. Ideally, these would have been waiting on the ground and not taken off. So this is one consequence of what happens when demand capacity balance is not kind of well measured. So here's this is another kind of bad day at Dallas. What you're going to see here is originally they were departing on these two runways, but then there was a sudden unpredicted change in the wind. So now they have to depart on these runways. And what you'll very soon see is a giant line of aircraft waiting to depart this runway and a giant line of aircraft waiting to depart this runway. So again, here, a change in our forecast, a change in our predictions results in unnecessarily high congestion and delay across the system. So kind of physically, this is what I mean when I say kind of traffic flow management is super important. Okay. All right, now let's get to the math of all this. So one of the simplest models that we as researchers use when we try to think about how do I assign the optimal amount of delay is through what's called the ground holding problem. And this is a relatively simple integer programming model. So the decision here and the picture that I want you all to have in your head is there is one airport in the middle, and there are flights that are generated that wants to land at that airport at some time. And your job as the optimizer is to decide if you allow the flight to land at a certain time t. Okay, so that's the decision variable. So this is actually a binary program. And what you're trying to do is you're trying to make these decisions subject to minimize, you're trying to make this decision at some minimal cost. So maybe this is the cost of delaying the flights. Okay. And you're doing this subject to two main constraints. The first constraint is at every time t, you want to look at the number of yeses you've said, and that number of yes must be smaller than the actual capacity of the airport, the arrival capacity of the airport. This constraint, if you don't have this constraint, what this program is going to do, it's very smart. Okay, what this program is going to do is it's going to say no flights need to land ever. Okay, so it's just going to be zero. So it's going to give you the trivial solution of all zeros. So you need this constraint that says for every flight across my entire time window, you have to land it at some point. You don't need to land it twice, you just have to land it once. So this is kind of the simplest decision model for ground holding problems. There are more complex ones, like a multi-airport variant. There's also dynamic ones, stochastic. Anyways, there's a lot of variations on this problem, but this is sort of the simplest form that I can show you to motivate what I'm about to do to this problem, which is, okay, imagine that this capacity right-hand side comes from a prediction model. So I have some machine learning model that's telling me what is going to be the capacity at future time, t, okay? And again, remember, this looks like a number, but it's really not. It's a distribution, right? It's an outcome. It's an output of your prediction model. So it's going to be there's going to be some uncertainty in that. Okay. And the question is, how do I make decisions that are robust against not just the fact that it's uncertain, but that maybe it even got the distribution wrong in the first place? Okay. Okay. So this is sort of the kind of the basic mathematical framework, and we're going to go ahead and augment this a little bit. Okay. These are the two papers that this is based off of. I can send it to you offline. You don't have to struggle with taking pictures for URLs. But basically, I call this the math paper. Basically, if you take our formulation and you put it into Garodi or you put it into a solver, it will not solve. So you have to do some interesting reformulations. So this is the reformulations that we did. This one is what I call the data paper. So we actually work with Professor Li Shuai Li at City University of Hong Kong, where their team had a fantastic airport capacity prediction model. So we said, well, we don't need to reinvent the wheel. We can just take their prediction model's output, which is again a distribution, and we can robustify it and make decisions based off of that output. Okay, so great collaborations that we were able to exploit. Okay, some more math, and I'm so sorry, but we do have to talk a little bit about probabilities. So remember what we're trying to do here. The machine learning algorithm spits out a distribution. I want to make decisions that are robust against that distribution being a little bit wrong. So maybe it's actually another distribution that's some distance away, or maybe it's some other distribution that's some distance away. So the moment I start talking about closeness, farness of distributions, I need some sort of measure. I need a metric to describe how close or how far. Okay. So what I'm going to do here is I'm going to build up a certain kind of probability metric. You might have seen it. It's pretty popular in computer science and machine learning. But I want to give you a little bit of kind of fundamentals. So basically, we're looking at the same support. Okay, so the support of the distribution for us is going to be non-negative integers, number of aircraft that can land per hour, and you have some probability mass function on this support. Of course, there are infinite numbers of probability distributions that have that same support. What I'm interested in is some measure of distance. Again, this is just one possible measure. You can kind of think of this as the shortest distance between two probability distributions that lies on the same manifold, right? So there's some space where every point on that space is a probability distribution. The closest distance between 2 points on that space is not necessarily Euclidean. Okay, it's some different sort of geodesic curve, and it turns out the 2 Wasserstein distance is generally the right measure for the shortest distance between 2 points in a probability distribution manifold. Okay. Basically, think Q1 comes from your machine learning output. Q2 is some other arbitrary distribution, and you want to measure distances between those 2 distributions. Okay. What we're going to do is, all right, so again, P hat is the output of my machine learning algorithm. I want to look at all the distributions that are within some epsilon neighborhood of P hat. So that's basically this set here. It's a set defined through the distance measure using Wasserstein distance. Again, there's some nice reasons to use Wasserstein, but you don't have to. You can use total variation distance. You can use KL divergence. You can use other kinds of distance measures onto probability distributions. Okay. Okay, so I always like visuals. So I'm a very visual person. So kind of how to think about this is, let's say that's what your machine learning gives you. That in the next 3 hours, this is what I think your capacity at Boston will be. So that's our p-hat distribution. The way to think about what our ambiguity set is measuring is in the center of the set, that's what your machine learning gave you. Okay. This orange space is the space of all valid probability distributions on the same supports. And we're interested in some bubble within this space of size epsilon. And there's, of course, many, many other distributions that live in this green bubble. And now what we're going to do is we're actually going to set up an optimization problem where I'm going to optimize the cost function such that I find whatever distribution in this bubble gives me the worst possible cost. So what I'm essentially saying is I want to make a decision that is robust against the worst possible distribution that exists in this neighborhood. Okay. So some of you might already be thinking, well, this depends a lot on this epsilon parameter, right? If epsilon is 0, this actually collapses the stochastic programming because there's only one distribution. And then I'll actually show you that as a sanity check. If your epsilon is now too big, now you're going to get into a case of being potentially over conservative. Because maybe if it's so big, you're going to get a probability distribution that is much worse than what happened in real life. So in this case, you're assigning a lot of delays unnecessarily because you think something really, really bad is going to happen. But maybe it didn't actually happen. So this epsilon becomes very important to this distributionally robust optimization. So keep this picture in mind and kind of keep this epsilon in mind. So I asked just to give you some more visualizations, to give you some ideas of what this ambiguity set looks like. Imagine this is the output of your machine learning algorithm. And what I asked my student to do was to just generate a bunch of random Gaussians that live within a neighborhood of epsilon 0.005. This is a dimensionless parameter. This is sort of, it's not that meaningful. The only thing that's meaningful are relative epsilons. But these green Gaussian distributions are all inside of that ambiguity set. So if one of these Gaussian distributions has a worst case cost for your objective function, you're going to make decisions against that. But of course, it does not need to. So what I think is particularly nice about this framework is it doesn't need to be Gaussians, okay? Because of course, an infinite number of parametric and non-parametric distributions live within this ambiguity set. So here are all the other sort of distributions that also live within the same ambiguity set size of 0.005, okay? Now, some of these we probably will never use in air transportation. Like, I'm not quite sure what is modeled as a Laplace in air transportation, but others like log normal, so or gamma distributions, especially so gamma, you especially see in a lot of queuing systems. You start seeing these gamma distributions. Log normal is sort of a cheap trick to say, oh, well, airport capacities are never negative, so I'm gonna, hit the normal distribution with essentially a map that pushes it all into the positive half line, right? So there's kind of nice, what's really nice is you can, of course, handle all these other distributional families. Okay, so now what happens is, unfortunately, our objective becomes a lot nastier. So this is kind of the classical objective function for the ground holding problem. You want to minimize the cost of ground delays plus the cost of air delays. So this is typical. What we now add to make this distributionally robust is that for every airport, we have a capacity prediction for both departures and arrivals, and we robustify that with some ambiguity set, which is denoted by calligraphic P. And now we turn this problem into a two-stage stochastic optimization where you are interested in minimizing the overall cost subject to whatever the worst case cost is for your ground delay and for your air delay. And unfortunately, these two terms is what results in like a really, really hard problem to solve. So again, if you put this into your solvers naively, it will not solve this. So this is basically what the math paper is about, is how do you take these nasty terms in the objective and reformulate it, relax it, and discretize it appropriately so that you can actually tractably solve it. So once you go through this procedure, you could solve this for about 9 to 10,000 flights, 30 airports, 12-hour time horizon. It solves usually in about 15 to 20 minutes, which we would actually still like to do a little bit faster, and you'll see why we would like to do it a little bit faster in a bit, but at least it's solvable. Okay, before it would not solve. I won't give the details on the mathematics of this, but I'm happy to talk offline or see the math paper. Okay, so this is sort of the punchline of the results. What I'm plotting here is, this is the expected cost of your delay policy. So the lower, the better. This on the x-axis is the size of your ambiguity set. There's a typo, this should be 1.1. Anyways, so this is the size of your ambiguity set. The green line up above is the deterministic ground holding problem. So you say, oh, the airport is going to have 24 aircraft per hour as the capacity. You optimize your policy with respect to that. Then you actually implement it and you do pretty badly because you're not taking into account any stochasticity. The blue line is the result of the stochastic version. So you say, okay, it's not actually 24. It's a Gaussian distribution centered on 24. So I'm now going to minimize the expected cost. Now you do a little bit better. So this is the value of your stochastic solution. is that gap between the green and the blue. What is fascinating is if you do the distributionally robust version, when your epsilon is size 0, so again, a good sanity check is that this should collapse to the stochastic optimization solution, and it does, which is great, because the only distribution in here was the original distribution that you started with. As you increase epsilon, what's fascinating is that your cost goes down, because it seems that your actual experience distribution was a little bit worse than what your prediction had thought. So all of this improvements, where is that improvement coming from? That improvement is coming from you giving ground delays to flights that would not have gotten ground delays before and would have instead resulted in airborne holding. That's where that improvement comes from. Now, the second fascinating and kind of worrying thing is this part, right? Which is you are now de-improving, you're now getting worse, right? So what is this deterioration happening here? This deterioration is as you increase this ambiguity set, you are now taking into account worst case distributions that were much worse than what actually happened in real life. So now all of this deterioration is you assigning ground delays to aircraft that actually did not need ground delays. So this results in a formulation that lets us take what we started with 20 minutes ago in words and actually translate it as a mathematical statement. And what is really the kind of the higher lesson learned? If you trust your machine learning output, don't do this. Do the stochastic optimization. If you don't trust it, or if it's high variance, or if you think there might be something wrong with your distribution, maybe look into solving the distribution robust version. Practically, we now run into a challenge. Every time you see an epsilon here, we had to resolve the entire problem with a new epsilon. So every single point on this orange line is 15 to 20 minutes. Now you're like, oh, this is going to be really tricky to tune this epsilon. If it's going to take me 15 to 20 minutes to solve a version of this problem to get a solution, right? So some of the ongoing work, so this is very much an open problem. And this kind of encapsulates the problem. We want to find some epsilon star such that this expected cost is minimized. Okay. The first thing that we tried to do, that my student tried to do, is can you establish some monotonicity guarantee? So the moment you see it going up, you don't have to explore anymore. But actually, even in this example, you can tell that that's not true because there's some non-monotonicity right up here. So this is not, okay, so actually this turns out to be true for a simple news vendor type 2-stage problem. It is not true for this much more complicated airport ground relay stuff. So we kind of gave up here because we didn't really have any better ideas of how to prove monotonicity on this cost function, okay, as a function of epsilon. So then what we did was, because I mean we're all engineers in this room, right? So we just have to get it working, even if it's not kind of mathematically nice. The other approach is say, all right, you know what? Let's just give up and say, yes, we have to resolve it every single time for every different epsilon value. But if we can solve it faster, that's also okay too. If every epsilon takes me 1 second to solve, I don't really care. I can let it sit for 100 seconds and it'll sweep through the epsilon. So what my student is working on now is, can you come up with a nice approximation algorithm that smoothes the Wasserstein distance constraint? So this constraint is, and again, it's in the math paper, but there's a constraint that is really nasty that prevents you from doing things like gradients on this problem. So we have some interesting results. So basically, we said, okay, the airport problem is a little too hard for us. Let's just look at a 2-stage distribution robust linear program. And why this is significantly easier, mostly because this X is continuous. It is not binary. Right? It's a continuous decision variable. This constraint is the nasty constraint because this distance measure here is a Wasserstein distance evaluation, which is really hard to do. But my student is very smart. I didn't do any of this. The student found interesting ways to approximate this and prove that this approximation is actually optimal. So what we're able to show is here are different epsilon values. Here is the actual the LP solution. This is the approximated solution. So this is actually for the test problems that we've tried, this is actually an exact approximation. And the time for the solution is magnitudes faster than what solving the LP problem is. And of course, the LP problem is easy to solve. These are very short times as well. But we were glad to see the improvements in time. So what we'd like to do is to actually apply this to the multi-airport ground holding problem and see if we can also get this nice reduction, maybe from 10 minutes to a second or a minute, or at least some sort of reduction. Okay. And kind of, all right, the last thing that I'll say with this part is air transportation is becoming weird, right? Sort of problems in the airspace that we've never dealt with before. And if you've never dealt with it before, that's not a good thing for your machine learning algorithm because it has no data to train it on. Which means, should you trust your machine learning algorithm? I don't know, right? Maybe not. So in these cases, perhaps it is worthwhile thinking about how do I make decisions in this world where every decision is sometimes made from predictions, but how do I make it more robust? Okay, so that's really part one. What I'll do for the next 15, 20 minutes or so is to completely change topics and talk a little bit about oh yeah, this is just anyways. So and talk a little bit about some new operations and some new missions. So what you've heard thus far is basically this person, right? Commercial aviation. I'm going to talk in the second part about urban air mobility, about air taxis. So kind of envisioning a future that is not yet here. Okay. Maybe a quick high-level note. What I love about working in this part is the system exists. You can touch it, you can use it. However, what's bad about it from a research perspective is it constrains your solutions a little bit. What's nice about this part is there's no constraints. It's a blank slate. But what's bad is you have to, and this is something I know Professor Ewan and I were talking about earlier, you have to talk with industry. You have to talk with the people trying to implement this who can make sure that your solutions aren't too crazy. Okay, so on the second part, this is really a collaboration with again, this is also led by Hao Chen. I'm really working Hao Chen to death here. It's a collaboration with Hao Chen as well as our colleagues from the MITRE Corporation, which is it's a federally funded research and development corporation that does research for the Federal Aviation Administration. So all of the motivation and the funding for this project comes from the FAA, and the FAA wanted us to help them think about this problem of how do you do air traffic control and air traffic management when you have these things coming into the airspace. So today, air traffic control is one controller, one radio, one pilot, which obviously will not scale to these new vehicles at the densities that people are thinking about. And also some of them won't even have pilots, right? So you can't really talk to them, and others might be autonomously flown and so on. Okay. Once again, if you search things like UAS traffic management and advanced air mobility, airspace management, you'll see these very, very nice concepts of operations or CONOPS documents, which are essentially similarly to that FAA booklet that I showed you. Again, really, really cool ideas. It really makes me excited, but I look through them and I say, how do you actually do this, right? Like how do you actually implement this vision? And specifically for this setting, the vision is what's called a public-private partnership, which is I always find it funny giving this presentation to people in surface transportation, urban transportation, because private-public partnerships are everywhere in kind of the usual transportation planning world. But in aviation, it's not as common. So today in aviation, you have the central authority, so this would be the FAA in the US, they talk directly to the pilot, the flights, and so on. The vision for kind of the traffic flow management, air traffic control of the future is a more federated architecture where the FAA is not going to be responsible for day-to-day operations. What they want is they want companies to actually do the day-to-day management of the airspace and air traffic control. In practice, in theory, this makes a lot of sense. It leaves the FAA kind of free to think about kind of higher level strategies and goals. It gives kind of responsibility to companies to share in. However, there's also kind of really interesting problems that occur here. For example, there's nothing preventing a service provider from also being a fleet operator. So what that means is, maybe this is Supernal, and Supernal is also a PSU, a provider of service for UAS. Well, if Supernal is watching over an airspace, is it going to give priority to Supernal flights or other flights? It's going to give priority to Supernal flights. So there's some interesting sort of game theoretic stuff that could happen here. So we and the FAA is aware of this, and they're looking for mathematical models to help them think through some of these different scenarios. So that was sort of the job that we were given. If you go look at the ConOps, you will actually see a version of this diagram. And it's like, when you first look at it, it's like, oh, this makes sense. But then you realize, what is this? Like, what are these arrows? What are these interactions? How do you take this and move it into reality? Okay. So the best that we came up with, and I'm not saying that this is optimal, but it's a start. So we augment this into something that's a little bit more detailed. Okay. So the way to read this diagram is to follow my finger because it's not my finger. So how I would read this is you have, again, and this is actually a part that I think, Krista, you do a lot of work in, because where's the demand? Who actually wants to fly these? Where do I need to serve? Okay. So I assume you have some way to generate it. Now, that is then given to the private companies that's watching over the airspace, and they are essentially doing demand capacity balancing. They're saying, all right, this is the demand that needs to be served, and this is the aircraft that will actually service the demand. Which paths in the sky will you take? Okay, so this level is essentially a dynamic traffic assignment optimization. So this little loop happens every hour, every 2 hours, some frequency. So it's a day-to-day, day of operations. Now, every time you do this loop once, you get some delays, right? So you see that some people had to be delayed, some people had to be rerouted, and so on. So you get an outcome of one round of dynamic traffic assignment. What is the role of the FAA? What we said the FAA should handle is the FAA is looking at the system, and it's not going to go every day to change something about the system. It's going to wait. It's going to look at how the system is operating. Is it doing good? Is it doing bad? See how the system is operating. Then maybe once every month or once every 3 months, the FAA will kind of look at the outcomes of all of this decision making in the past month or 3 months or whatever the time horizon is, and say, there's a congested area here and a congested area here. I don't like those. How can I get people to stop congestifying those areas? Well, one thing is to change the demand. That's probably pretty hard. I don't know how to do that. The other thing is to make it more expensive to fly through, right? So this is the classical idea of congestion pricing. It's saying, okay, I don't want congestion here. I want you to spread out. How do I increase your disutility of going through these congested concepts? So that's really the high level loop there. Okay. And so on the low level planning, so again, on this part, this is really just a scheduling and routing optimization problem. Okay. And I'll show you the formulations. It's a lot of math, but just read the works. So this is what's being run on the low-level planner every hour or every 3 hours or 4 hours or whatever. And what it's doing is, this is what the PSUs would run after they receive the demands and they receive the airspace capacities and path capacities and so on. So they're going to try to minimize, some costs, subjects to you can't, basically these are separation constraints, right? So 2 aircraft can't be too separated and so on. Of course, there are lots of interesting, for example, if we wanted to be more sophisticated, maybe this is a geofencing based constraint. There's different ways you can fancify this constraint here, but this is sort of the most rudimentary. It's just a separation constraint. And then we have some, just some more basic, there's costs that you need to adhere to. If you choose a certain edge, it's going to cost you. If you want to land at this vertiport or that vertiport, it's going to cost you different. So when the low-level planner is solving this, all of the costs are fixed. So the edges have a certain fixed cost. The vertiports have a certain fixed cost. They're all fixed, okay? These costs are not changing between runs of the low level. And that's because they will change when the high level planner tells it to change. So this is being run, 7 times a day, 8 times a day, whatever the cadence needs to be, okay? So what is the high level planner doing in this case? Oh, actually, what is the high level planner doing in this case? Well, the high level planner is looking at kind of a summary performance of that low level optimization problem. And it's saying, do I need to do some congestion pricing? Do I need to do some tolls? Okay. So the high level planner basically has 2 main mechanisms. They can change the price on the edges, and they can change the landing fees of the vertiports. So those are 2 of the pricing mechanisms that we give to the high level planner. And this slide here is just to say, well, if the FAA doesn't want to price vertiports, we can get rid of that. Or if they want to price something else. So there's lots of flexibility that we can explore. We just kind of chose a very simple case. And so the high level planner, again, once a month or once every 3 months, is solving this optimization problem once. And what this optimization problem is again, we gave it a very simple objective. You're just trying to minimize the congestion across your network. So all that delta A tau is, it's just a measure of congestion at different pieces of my airspace. The mechanism with which you have to do this is by changing, again, the costs on the paths and on the when you want to land at a vertiport. So this is a classic bi-level optimization. So this is the outer layer. This is the outer optimization. And then the inner optimization was that thing that I showed you a couple of slides ago, that the low-level planner runs. So now what makes this really challenging is that the high-level planner needs to make decisions that still result in feasible low-level planner solutions, or you can't make a decision that results in an infeasibility in the inner problem. So there's actually a bunch of constraints that I'm not showing here, which is coming from that other problem. Secondly, your high-level problem needs to make sure that the decisions you make is still optimal for the low-level problem. So now this constraint, this might look very familiar. That is actually the objective function of the inner problem that you just saw. So that what you see in that constraint is exactly the objective function of the low-level problem. Okay. So actually, let me keep this here for a second. This problem, the low-level planner is actually, despite looking nasty, it's actually pretty easy to solve. So essentially, it's a mixed interlinear program. It has a nice convex relaxation. You can find the optimal solution pretty quickly. Very nice. Okay, so you essentially, in a very, if these are, so this is low-level decisions, and this is the objective function of the low-level problem. Okay, and at some point you get something that looks like this, and you can find the optimal. What kills this problem is once you go to this, once you want to solve the high-level planner, what you're essentially doing, and this is the way that I like to think about it, what you're essentially doing is you're adding a third axis, where the third axis is the high-level decisions. And so for each high-level decision, so what is a high-level decision? It's a set of pricing policies on your vertiports and on your edges. So for each high-level decision, you get a curve. And for another, you get another curve, and so on. So you get a surface, right? You get a surface of objective function values. Again, I can't really draw this, but imagine this surface, this 3D surface. This surface is highly non-convex with respect to these decisions, which means this is now a nonlinear integer program, mixed integer program, and it's not easy to solve. In fact, it's very difficult to solve. We cannot solve this very fast. So we tried for a very long time, and again, the annoying constraint is this one. This is really the nasty constraint here. So we really tried a very long time to, can we reformulate this? Can we relax this? Can we what can we do to solve it? And finally, we sort of gave up and we said, well, we can approximate it. Right? That's maybe the best that we can do. So the idea here is as follows. This surface is something really weird and hard to work with. I don't like it. What I'm going to do is I'm going to try to find some convex function, which is convex, with unknown parameters. And I'm going to try to train a neural network to give me the parameters of this convex surrogate. So essentially, I'm trying to fit a weird convex function, but I'm trying to fit it as closely as I can to this surface here. Okay. It's not going to be perfect. In fact, it's probably going to be really bad of an approximation at the far edges. Okay, but at least it's convex and I can solve this problem. So that's exactly what we do. So the procedure is as follows. So this is becoming a more and more popular method in optimization, which is using these neural network surrogates. Okay. So the idea is as follows. What I'm going to do is I'm going to solving individual instances of this problem is still nasty, but it's not as bad. So if you choose a fixed pricing policy, you can find the optimal on the low level plan. Okay. So now imagine we now have a big list. So we have let's say pricing policy 1, and then the low level planner, and then you have a low level planner optimal value 1, pricing policy 2, low level planner 2, and so on. You collect, let's say, n equals 1,000 of these samples. These are essentially the training samples for your neural network. You say, well, this is the function. Somehow this became that. Okay, I want you to find the phi that makes it as close as possible. There's actually some. Unfortunately, this is not just one dimension. This is actually a pretty high dimensional thing. So you can't just naively sample. We use like some Latin hypercube sample. Anyways, there's like a sampling strategy that is not bad here, and we fit it into. So what we put this back into the program, and this is sort of the second necessary step. You train a neural, so I don't know how many people here have worked with neural networks, but essentially, you choose an activation function, and then you are looking at the weights and bias of the different layers. Well, you have to put that into the objective. You have to put that into an optimization function somehow. So what you can do is, and this is a really neat trick, especially if you use a ReLU type network. So this is that phi hat that is going to approximate the surrogate. That's going to approximate the real value function. But you need to make sure that this phi hat behaves like your trained neural network. So what you can do is you can put in your neural network into the optimization. So you can force the final output of phi hat to match the outcomes of your neural network. And what's even better is all of these constraints are nice and linear. So these are not nasty constraints, especially if you use ReLU networks, because you can kind of decompose the flat part and the linear part and so on. So this to me is almost magical because you can take something as complicated as a neural network object, but you can force it into a optimization problem. And now this phi hat is nice and convex. What I realized is I didn't actually. Okay, so what does this look like? This is my last slide, research-wise. So what does this look like? We tried this on kind of a real network of, well, not real, these aren't built, but on a case study of Los Angeles. We instantiated a couple of vertiport locations. We used a very basic k-means on top of some populations, of course. And actually, this is where I think there's very interesting conversations of how could we use some more sophisticated vertiport planning models. Our paper was not about vertiport planning, so we just used like a basic model. So what you see here is we have these vertiports, we have 84 routes, a bunch of flights, and the outcome, if you don't use the high level congestion pricing, you get kind of hotspots that built up around these airspace sectors over here. And this big gray thing, this is actually the class Bravo airspace of Los Angeles International Airport. So you can't actually fly through it. So then, so we kind of expected this to happen because, you know, this is kind of a heavily trafficked corridor. So a lot of people want to kind of hug as close as possible to the class Bravo airspace. Then after we congestion price, so after the FAA says, whoa, I don't like this, there's too much congestion here, what you see is some other places the congestion increase, the congestion increased, but you get a much reduction of the hotspots that used to be there from before. And you can see it more clearly in the bottom two, where this one shows you which sectors had a decrease in traffic. And the heaviest decrease matches the heaviest congestion from before. And of course, everything else surrounding it, because you've now congestion priced either of these edges, slash maybe even some of the vertiports, you get increased traffic in some of the other sectors now because they're taking a slightly cheaper route. So what's great is that we can now let kind of the congestion pricing policy tell us exactly how to spread traffic, right? How to do this balancing in traffic. Okay, so with that, I just wanted to conclude by saying, okay, thank you to the sponsors. Otherwise, we can't do this research. And then more importantly, so I have a fantastic group of students. Actually, I think Jimin is from Heights, so she did her master's and bachelor's here. I actually met her the last time I was here like 2 years ago when I gave a talk at Jinhu. Yeah. So love the school. Unfortunately, I didn't really talk about her work. She does more on the kind of autonomy and drones part. Yeah, so thank you for letting me blabber at you for an hour. I'm happy to take questions, and I think my train's at 6 o'clock, so I have some time before I have to go. But thank you so much.
Do you have any questions? Any questions?
A general question. Thank you so much for the talk. The first part and the second part was really interesting. How imminent do you think it's the future of uranium studies? And it's amazing that we're already doing a lot of the groundwork for it. It's amazing future we might be able to, but how soon will we see some sort of movement in the United States? I see that in San Francisco we're having some sort of autonomous taxis happening. What do you think UAM is maybe the next field that we're entering?
Yeah, that's a great question. And your answer really change. You know, if you ask people from McKinsey, from NASA, it's a different answer than people. For example, I think you see China prioritizing the low altitude economy. Right? So there's sort of a big push there to get some of these air taxis going. I think in the US, it needs to be economically sensible for the companies to run it. And sometimes I read so many things, I don't know what to believe, but what I do think is true is I don't think you can make a profit on these without making them autonomous. Because if they can only sit 6 to 8 people, having that marginal seats open up, if you don't need a pilot, is going to be very important. The problem with that is it's really hard to certify autonomous flying things. Even though actually I think autonomous flying is actually an easier engineering problem than autonomous driving, because on the streets you can have a kid come across the street, have a cat or whatever. In the sky, there's not too many things. Okay. My estimate, autonomous drones like delivering stuff, etc. I think you can probably see that. I would say it's like early 2030s, mid 2030s. I don't think we'll have like widespread air taxi operations outside of a couple of niches until maybe 2040 plus, just because of the level of autonomy that's required to be certified and verified. But yeah, so but I think it's, but then if you think about like, if you look at what airlines are doing today, it's basically air traffic management research from 15 to 20 years ago, right? So sort of there's this lag, right? So we can't really afford to not be at least 15, 20 years ahead of industry, because then they're going to get there and be like, oh, there's nothing to refer back to. So that would be my answer. I think you had a question? Yeah.
Thank you for the talk. It was very interesting. I was not really familiar with traffic control and algorithms, but so the question that I have was, I was interested in the second part where you first saw that optimization. And then, so on that law, is it like, are we approximating the optimal value at the low level with respect to high level decision, or are we just getting all the one?
So mathematically, I want to be able to optimize a surface across this axis. So I'm approximating the surface so that I can do gradient descent on it with respect to the high level decision. So the approximation is the low level objective function, but now instead of the prices being constant, they are variables. And the low level objective is not convex with respect to those new variables that you introduce. Does that make sense?
So my first intuition was, I thought, I guess because you have to solve the low level problem for every change in high level.
Correct.
Right?
Correct.
So
yes.
that makes it really hard to solve the
It's hard because the low level planner itself is convex in the low level decisions. For a fixed, so if I vary the high level decision, but then I fix it, if I fix it, it's still convex in the low level decisions. But this thing is not convex in the high level decisions. And that's why we have to approximate it in the direction. Again, this is just the visualization, right? Really, like there's like 7 dimensions, right? So it's non-convex in the essentially the basis vectors of the high level decision variable. If you want to think about that. Yeah. Thanks for the question.
About the first distribution.
Yes.
I'm wondering if you think it's possible or feasible to apply it to the real airport setting, because in that case, the input data distribution would be changing.
Yes. Yeah. So even in our model, the distribution changes as a function of time. So so like Professor Li Shuai Li's group gives us a prediction for the next 12 hours. The distributions, actually, and in fact, I have a picture of the distributions here in my additional slides somewhere. So actually, this is what she's giving us. So each row is a probability mass function, right? So each column here is a distribution. So you can see it does change throughout the day, right? So we're making a decision at, let's say at this time, we're making a decision for the rest of the 12-hour period, let's say. So there is going to be variations in the airport capacity predictions. Your question about implementing this in real life is really interesting because air traffic controllers are not data scientists. Okay? They're not like, you cannot show them this and be like, make a decision based on, okay, they're not going to do that. I think what could be interesting is depending on the predicted weather, within the computer, it runs this DRO and it tries to figure out an optimal solution, and then it suggests a policy. Like, hey, Delta 123 gets delayed, 10 minutes, that gets delayed. So if you suggest a policy in language that the air traffic managers are used to, that's feasible. But you cannot show them like the DRO solution with epsilon equals to 0.05. It's not going to make sense to them. That's not what their job is.
Yeah, I remember when I was a student working with SFO and tried to predict the AVI and API.
Yeah.
Because we have convective weather there all the time. And I asked Mark can I visit the air traffic control tower to talk to the controller. So we got the permission and then I get to talk to them. And I realized we were doing all this sophisticated research, but what they resort to is just one little memo.
Yes.
Yeah, if this is the weather condition, this is the 60s.
Yeah.
If this is the weather condition 28, you close down, it becomes 30. So this is like a 5-line little memo they looked at. So I was shocked. I was totally shocked. But things have changed so much, and especially once we get into a lot more like air traffic in the America, it's just impossible to just rely on
Exactly.
but we have to have a bit of autonomy,
Yes.
even for the control. So I think the research that you're doing is really critical, especially for the very busy and the short haul traffic.
Yeah, and what's really interesting is even air traffic controllers, they have played with ChatGPT on their phone. They're like, oh, there is something different, right? Like this is like, if this is so useful for me in my everyday life, why can we not have this in my work, right? So actually, some of the I think they are becoming more and more open to like, we don't need just a paper memo or we don't actually some people will say that, well, a similar story is basically like, we were trying to figure out like what is for a jet routes, I'm going to give you the probability of it being closed. So 47% chance that it's closed and so on. And then we talk to the controllers and they say, no, I just want red, yellow, green.
Yes.
Okay, green is open, red is closed, yellow is depending on how I feel that day, I'll open or close it, right? So it's, it's so I think I think you're all civil engineers for aero. You're going to be working with folks in industry who have to make this work in real life, right? So I think there's sort of an optimality gap in some sense, right? Of like implementability and perfection, right? It's some numerical perfection. And I think that's been an interesting conversation.
Any other questions? I actually have one question, kind of comment and one question. So in the slide 44, for your first presentation, the table looks really, really pretty clean.
This one.
Yeah,
Oh, yeah.
because the LP time, if you see there's a lot of variation. It's sometimes 0.6, sometimes 0.0. But once you have your algorithm, it's more like a lot more continuous. So I really like the that was pretty nice. And the question that I had is about the last slide that showed us about protection pricing. It's a 7 day. So one thing that some in here worked on in terms of vertical integration is that the way we look at the same problem is that, if there's going to be any congestion expected, can we place the vertical and distribute the network a little differently so that we can reduce congestion not compromising the travel demand, travel time too much, but people don't have to spend money or to spend money to fly certain the corridor. Is there any are there rural people who's looking, the same like in the US?
No. No, I think most of the vertiport research that I've seen in the US focuses on like, if we put a vertiport here, there might be more noise here. So how do we think about kind of the distributional impacts of vertiport placements? That's a really, so essentially what you're proposing is like almost like flexible infrastructure. When there is congestion, perhaps you open another vertiport where you close one and so on. That's really creative because we usually we just assume vertiports are fixed, right? We say, okay, this is the vertiport. There's no changes and whatnot.
So the voting patients are already well planned for this.
No. So this is fake. So all of the stars that you see here, these are just fake vertiports. Okay. I think the concept of operations is we're first going to use existing heliports. So I guess you could, in theory, you could map out the existing heliports, and I think NASA has a couple of studies that look at if you have these heliports. What's interesting is there's one of these companies, Archer, is a AAM company, and Archer released a very interesting memo about their plans for the 2028 Olympics. So everyone's very excited about the Olympics because they're in LA. Yeah, so they're in LA, and I think the FAA wants to do air taxis for the Olympics. We'll see if it happens. But Archer said, some vertiports might be exclusive use. So only Archer can land and take off there. Nobody else. So Supernova cannot, Joby cannot, and so on. Why that's interesting to me is essentially if you have a exclusive use vertiport, it's actually pretty easy to represent that in the optimization. It just becomes infinite landing costs for everybody except for a subset of the flights that belong there. How will that change the solution? I don't know, right? Like that's there's, as far as I know, there has been no widespread building and siting planning of vertiports in the US. So I think there's still a lot of room for research and creativity.
Well, I was thinking, there's a pricing part that is already done, and maybe we can add another, throw in another component of verification and how it changes the number of flight it can serve, how much of the congestion pricing impact is going to increase or decrease and things like that. So that could be another.
Yeah, and like I said, we use a very basic demand model. So if you all have ideas about demand estimation, that would be a great way to collaborate and see how this changes with a new demand model. If you all have ideas about vertiport placement and have that be an additional variable, there might even be new things we have to do here to make the vertiport placement problem trackable in this setting. So that would also be a great line of collaboration. We have this pricing model, the congestion pricing model, and I'm sure Hao Chen wouldn't mind another paper. So that's always the motivation, right? But yeah, thank you for the question.
Thank you so much. Just finance and any other question?
Or I guess online. I don't know if people online have questions. Okay, there's no. Okay, good. Thank you for tracking.
Thank you so much.
Thank you. Oh, thank you.